Today I'm going to show you how to solve a half-wave rectifier circuit. So let me share my screen. So for this one, for half-wave rectifier with resistive load. So this is the question, and I'm going to solve this question using LTS spice. And here it has solution over here. The book name is Power Electronics by Daniel Hart. So the question is this one. For the half-wave rectifier of figure 3.1a, the source is sinusoid of 120 volt RMS at a frequency of 60 Hz. The load resistor is 5 ohm. So it's asking find the average load current. And in B, the average power absorbed by the load, and in C, the power factor of the circuit. So let me show you the circuit over here. So this is the circuit. The question is talking about this circuit. So we have sinusoidal voltage source, which is the magnitude, the RMS value is 120 volt RMS at 60 Hz source frequency. And this is the diode. Yeah, we are assuming the diode is ideal. And it has the load is resistive load, pure resistive load. So let me go to LTS spice. So here the circuit is over here. I have already built that circuit. So let me make bigger. So for the 120 volt RMS, when we multiply by the square root of 2, we are getting 169.7, and I just rounded to 170, like 170 at 60 Hz. So maybe how we are. So here we are using sinusoidal voltage source. For the DC offset voltage, it's 0 amplitude, which is 120 multiplied by square root of 2. The source frequency is 60 Hz. So this one is, we are assuming the ideal diode. And for diode coefficient, the resistive load is 5 ohm. Let me show you one more time. So here the load resistor is 5 ohm. And the voltage source is 120 volt RMS at frequency 60 Hz. So let's go over here. So we are going to just transient response. I have set up the transient response at 100 millisecond. So how we are going to set up diode here in edit simulation command. So for transient response, the stop time is 100 milliseconds, which is 0.1 second. So this is R1, the load current. So I have already divided by pi to get average load current. Like, let me show you. for this one, suppose I'm just deleting the pi divided by pi, and we are just using cursor 1. So right now, let me have the cursor 1. So here, the current is almost 33.758. So which is 5, like, let me show you the voltage over here. So the voltage is almost 168.79. Still, we are assuming ideal source, but we are not getting 170 volt over here because this is not perfectly ideal. So this is just theoretically we are assuming the diode is ideal, but not in practically it's not ideal diode. So there is some kind of voltage drop over here. So right now, this is the half wave rectifier circuit, and this condition, it's showing the diode is forward biased. It means what we have voltage over here, we are also getting the voltage over here. So this value right now, the value for this one is it's giving the magnitude of the peak magnitude. It's like peak amplitude, which is almost like 168.79. So for that one, the voltage is the output voltage should be the average of sinusoidal, the rectified, so average of uh, the rectified sinusoidal voltage. The average voltage is nothing but the peak voltage divided by pi. Let me show you the theory over here. So here, so the voltage across the resistor is half wave rectified sine wave with peak value, which is 169.7 volt. And the average voltage is Vm, the peak voltage divided by pi. And average current is this one, just divided by pi, just divided by R. I mean, the average voltage, the output voltage divided by R, output voltage is nothing but it's the peak voltage divided by pi. So this is, we need to prove if we get 10.8 ampere as output current using LTSPI, then our goal for this question is will be fulfilled. So let's go over here to LTSPI. The voltage right now is 168.79. So we need to change this voltage. We need to divide by pi. So I'm just dividing by pi to get the output voltage. This is average voltage of this rectified sinusoidal voltage. So right now I'm getting 53.728 volt. So we can calculate over here also, like, so 169.7, which is peak sinusoidal voltage, the source sinusoidal voltage. When we are dividing by pi, so we are getting like 54.0202 volt. We have like before we had like 168.78, right? And right now dividing by 5, we are getting 53.728. So this is the output voltage. Now we are going to see the output current. So the output current is, so this is the peak current. We need to divide that one using, we need to divide that one. Yeah, it's good. We don't need to change. We need to divide this one by pi. So right now we have 10.745 which is almost 10.8 ampere, which is here. The solution is also 10.8 ampere. And in question number B, they ask you to find the average power absorbed by the load. So for average power, the power absorbed by the resistor, they are using V square RMS voltage. We know like the power is nothing but the voltage square of voltage, like basically in the RMS divided by the load resistor. So the power is like 1.44 kilowatt. So now we are going to see the how much we are getting the power in LT spice. So we got a power. So this is the power. So this is the power. So the power right now we have like this much, but we need to divide this by pi. So we have 1.8 kilowatt. Let me go over here. So the here power is almost 1.44 kilowatt. So the what we are getting, that is not correct. So then what we need to see over here for power. So the power we are seeing over here, it's like 1.8 kilowatt by dividing by this. For here, we need to divide by 2 pi. I mean, pi square to get that exact value. Hold on. No, we don't need to divide by this one, but I think we need to multiply by a square root of 2 to get like IRMS. Yeah, we need to multiply by a square root of SQRT, like a square root of 2 and a square root of 2. So let's go over here, I think. Just let's do over here. So the voltage over here is this. So this is the power. We are getting like 5.6998 kilowatt. Now to get exact power, so these voltages are in like peak voltage. So these are in peak magnitude for both voltage and diode. To get diode, we need to divide by 2. So 2.85 kilowatt. I think I'm missing something. So the power. So the power is this one. So the power is showing that much. You get an average power. To get an average power, they are just utilizing VA square RMS divided by R. We can do that one, but right now I'm trying to just use the graph to get the average power. So this should be, I think, how much is, so V output, let me go over here, maybe we can see this voltage 168, the voltage is 168 volt, and the current is like, I put the cursor over here. The current is almost like 33.69. So let me calculate this. 33.699. 699 multiplied by 169 point. How much we have over here? Oh, we have 168.499. 68.499. So we are getting like what? Like we are, by calculation, we are getting like 5.678 kilowatt. And by just putting cursor over here, the power we are getting, yeah, the power we are getting over here, which is almost 5.678. Yeah, I'm also getting that power. So for the bridge voltage, what we are getting, and the voltage and also the current and the power, these all are in peak magnitude. To get that in regular, like in DC magnitude, no, for that one, I think we need to just divide by the for pi. This is the pi and this is the pi. Like when we divide this one with pi, and also here divide with pi. This voltage is nothing but pi square, so pi square. Let me have some stairs. Let me use just, and this is the power. So yeah, the power is like, yeah, the power is 5.698 kilowatt. So these powers, it's showing this power in the what do you call, it's in peak magnitude. So how much here would they have power? Power absorbed by the resistor. Yeah, the power should be this much. I not VRMS. Or the VRMS square divided by R, or maybe we can do IRMS multiply VRMS. So over here, Divided by root 2, divided by root 2, divided by 2. So it should be over here like 2.84. Yeah, it's a square b r square. Just multiply by. For that, I'm using how much we have here. Yeah, it's like 1.44 kilowatt. And here we have 1.424 kilowatt. And that should be go, I think. Yeah, well, here I think we need to just divide by 4 to get the average power, because these are in peak value. So we just need to divide by 4 so we can get the average power. Or in other word, in other method, we can just, we can utilize that the RMS voltage. Like, for example, we have voltage over here 168.8. So this is 168.8 divided by square root of 2. This should be close to 120 volts. So we have here 100 119.3596 volt. So we can just square of this and divide by just 5. Oh, not this one. We need to divide by this with 5. Yeah, we need to divide with 5. And then we get 53.73. Then this is the peak output. Then we need to we need to divide by root 2. So how much we have 168.8 divided by root square root of divided by pi. So we can get 53.73, which needs to divide by the square root of 2. So we can get almost 38 volt. The square of that divided by 5. Still, we are not getting that one. So how they are finding? So they are utilizing just Vm over root 2. Vm, the Vm divided by 2. Yeah, it's same thing. Yeah, Vm divided by. So they are just utilizing that one. I mean. So Vm is this one. This needs to be divided by root 2, divided by 2. So because this is a half wave, that's why they are just dividing by 2 the peak voltage. So here, so here we have 120 divided by the square root of 2 to get the VRMS. VRMS for the rectifier, the half wave rectified sinusoid voltage. And that needs to be squared and divided by 5, so we can get the power, which is almost 1.44 kilowatt. So here they have also the RMS current in the resistor is Vm divided by 2R, because this is half wave. So Vm divided Vm is Vm divided by 2R. So Vm is 169. Here we have 168.8 divided by 2R, which is 10, which is like 17. We have like 16.88. And we need to, and the power could also be calculated from I square RMS R. Yeah, for that one. And we had the current that one, like 17. We can just square that one. We can square that one. We can square that one and multiply by 5. So which is like, yeah, like for me, I have like 1.424 kilowatts. To get a power factor, we are going to just divide by P over S. V as source. So source, which is like 17. So 120 into 17, like 14, 1.44. And divide by, and then we have VRMS 120. And we have our IRMS current for the source. We have 17, we have 16.88 exact value, 16.88. So dividing by this one, we have power factor of 0.71. And yeah, 0.71. Maybe we can find the cosine inverse of that one, like 45 degree power factor in angle form. So yeah, so this is the solution using that one. So one more time, so this is the alternative technique to find the current, the IRMS current in the resistor. Like for, since it is half wave, so basically we are just dividing the peak voltage by 2, and to find a IMS current, we are dividing the IRMS for the output. So Vm divided over 2R, which is like here with 17 ampere. The power could also be calculated from this IRMS multiplied by R, and the afferent voltage, which is the source voltage, RMS source voltage, multiplied by RMS current, which is this voltage. So the output current is 10.8 ampere. The VRMS, the RMS voltage across the resistor for a half wave rectified sinusoid is just Vm divided by 2. So Vm is nothing but it's 120. The IRM, the VRMS, the source voltage in RMS multiplied by the square root of 2. Since it is half wave rectifier, we are just dividing by 2. So we're getting 84.9 volt by theoretical. And the P, we can just power absorbed by the resistor, which is just the voltage RMS across the resistor, the square of voltage across the resistor in RMS form divided by R, which is like 1.44 kilowatt. And there is alternative technique method to find the average power consumed by resistor, which is 1.44. By finding the current, the RMS current in the resistor, and power factor is nothing but average power divided by apparent power. So we can get in. We got 0.707 theoretically, and I got how much? I got 0.71, which is a little bit different than the theoretical value. And power factor in terms of cosine of theta, we are getting like 44.69, which is almost by rounding nearest 10, like 45. Thank you. Thanks for watching.